In this section, we will see Taylor series and a particular case called Maclaurin series. You will see it's quite straightforward in terms of computation. Just some reminders. We have already seen some power series for certain functions. So the power series is unique. We remember that C is the center of the series. So here, when we have a convergent power series, it converges to certain function on certain interval. That interval is called interval of convergence. What we will see now is a reverse process where we take certain function f and then we use some formula, essentially the derivatives, as a special formula to create a power series. And that new power series that we create from a function f or using a function f is called Taylor series. Now Maclaurin series will be a Taylor series with center C equals 0. So that's a special case. When C is equal 0, then it's called Maclaurin series. So as usual, this Taylor series will be a power series, and then we need to find the interval of convergence using the ratio test as usual. Now what we will observe is that when we take a function f and we generate a power series, that power series is called Taylor series, and Taylor series is the power series also for the function. Reminder of what we have seen already. This is our fetish series, so it's power series also, it's also geometric, and this is a function f. So this function f is equal to this power series for x between -1 and 1. We have already seen this. So as we see here, the center of the series is 0. Now we have also seen an example how to get series for this function. Essentially we replace x by -x and then we get this term here. So this is a function f and its power series is also called Taylor series, is here, directly obtained. That was seen already. Here is the series, power series, or the Taylor series for the log 1 plus x. So how do we get it? Well, if we integrate this series here, we get this series. Simple. So essentially we integrate, and you see here we started at 0. When we rewrite things, we start from 1. So essentially those are things that we have already seen. This one is also known. So here we replace, instead of x, we put x squared, and then we get another power series, which is also a Taylor series, and we have interval of convergence. We remember that if we integrate the right hand side, we'll get tan inverse x, which will be equal to the integral of the series term by term. We remember that the power series, we can integrate them term by term and differentiate them term by term. Same thing is true for the Taylor series. Now this is just a summary of some of the Taylor series that we will compute. So we will find the Taylor series for exponential x, for sine and cosine. We remember that if I have a series for sine, if I differentiate sine, I get cosine, so I can simply differentiate series for sine and I get the series for cosine. Simple as that. What we will see also is that we can have for each function several Taylor series depending on the center. So you see here the center was 0, so x minus 0, but here the center is pi over 2. So we have a different Taylor series, or as a power series, centered at pi over 2 for the same function sine. Actually, each time we change the center of the series, we get a new Taylor series for the same function. So basically one function can have infinitely many Taylor series. Log x, we already saw log 1 plus x, so we replace x by x minus 1 and then we get this simply. Tan inverse, as we said, we can integrate this series here and we get tan inverse. So the function is here and its power series, now called Taylor series. Now again, here the center is 0, so we can even say this is a Maclaurin series for tan inverse. So this is just introducing new names for the things that we already know. Obviously, each of these series, power series, Taylor series, Maclaurin series, is equal to a function on a certain interval. So we need our interval of convergence, and we get it by using ratio test on the expression of the series. An observation that will be useful to show a result that is important to see. So this is something that will be used often. If I have a power series like this, I can use ratio test to find interval of convergence. So once we do that, we will realize that our series is absolutely convergent for all values of x. Obviously the sign doesn't change anything. So by the ratio test I can prove that this series is convergent, absolutely, and also for all values of x. The fact that the series is convergent, we remember, it means that automatically the general term of the series goes to 0 when n goes to infinity. So the limit of the general term as n goes to infinity of the general term is 0. The limit of the general term is 0. So that comes from the fact that the series is convergent. When the series is convergent, its general term converges to 0 when n goes to infinity. So that's important. You see here the fact that c is a number, right? So it could be 0, it could be 7, minus 55, doesn't matter. So this expression is converging to 0 when n goes to infinity. So we essentially have x to power n divided by n factorial. Now, the Taylor series as in the formula, you see it's straightforward. So we have here the general formula for the Taylor series. You see it is a power series. We need to use a function f. Ideally, the function f is infinitely differentiable, because you see here is the summation, and here we never stop. So we need to have many derivatives. So essentially, type of functions that we use is sine, cosine, tan inverse, some ratios, and exponential, log. So the things that we all have already seen. So this is a formula for a Taylor series, which is also a power series, generated by a function f centered at c. So the c is the center of the series. So you see what we have here is x minus c to power k. So this is giving us our power series. And the coefficient here is very special. Downstairs you have k factorial. And in the numerator we have the derivative, k derivative evaluated at the center of the series. So upstairs we will have a number, downstairs we have a number. So this is a coefficient in front of x minus c to power k. So this is a special formula that produces Taylor series given a function f and the center of the series. Now the special case is when the center is 0, then the series is called Maclaurin series. So we evaluate the derivatives at 0. So essentially what happens is c is 0, so x minus 0 is x, and derivatives are evaluated at 0. So that's why it's called Maclaurin series. It's a special name, nothing special, it's just a Taylor series with the center 0. So sometimes the question will just come saying find the Maclaurin series for a certain function. So you need to know that actually the center is 0 and you need to evaluate the derivatives at 0. Now this is a formula. We will get a series, the power series obviously, called Taylor series, using the function in the center. So we will need to see where is this series convergent. So we need to find the interval of convergence and the radius of convergence. How we do that? Using the ratio test. So we need to do it for each series. We need to do the work using the ratio test to find the interval convergence and radius of convergence. So by then we will know that on that interval convergence, the series that we generated, so the Taylor series, is convergent, which is great. So the question now, it is convergent to what? Well, it's convergent to some function. Okay, what is the function? Well, hopefully it is f, because we used f to generate the series. So essentially, if I give you sine of x and I say find the Taylor series for sine of x centered at pi over 7, well, you generate using the formula here, you generate the series. Then using the ratio test, we will find the interval of convergence. And now the last question is, well, that beautiful series is convergent to some function. Great. To which function? But hopefully it's function sine x, because I used sine x to generate the series. So that needs to be verified, and we will see the condition that we need to satisfy for that. So basically, the application of this is straightforward. We have a power series, and then we will have an interval of convergence that we will get using the ratio test, and we will essentially have a power series here. Now, just to see how we got the formula. So if I have this power series that is convergent on certain interval, if it's convergent, then it converges to certain function f. I don't know what is f. So I would like to know what is here the coefficient bk. What's the shape, essentially? So you see here, we just expand a little bit. What we realize is if we evaluate this expression at c, so x equals c, I have f of c. Here will c minus c is 0, c minus c is 0, squared is 0. So everything will be 0 except the first term. So suddenly I realize that f of c is equal to b0. So I got the b0 coefficient is equal to f of c. Beautiful. Now the question is, what is b1? Well, we know that the power series, we can differentiate both sides. So the derivative of f prime x is equal to the derivative on this side, term by term. So b0 will go, we'll have b1 plus 2b2 times x minus c, etc. So basically, again, we will evaluate at c, and then we will see how it goes. So basically, the idea is to use the fact that the derivative of a power series is also a power series. And now this is the expression. If I evaluate f prime at c, plug x equals c, so this is 0, this is 0, this is 0. So everybody is 0 except for b1. So b1 is equal to f prime at c. Wow. Then if I differentiate this thing, I get f prime prime, so second derivative. So b1 is gone, and I'll have 2b2. And then here I'll have 3 times 2 times b3 x minus c, etc. So, and then I will evaluate it also at the x equals c. So this is what I get when I differentiate the second time. So if I evaluate this at x equals c, so this is 0, this is 0, everybody is 0 except for the first term. So f prime prime at c is equal to 2b2. So I can get b2 is f prime prime at c divided by 2. That's beautiful. And then I keep going like this. So I keep differentiating and evaluating the derivatives at x equals c. So that way the remaining parts will be 0, and then just the first term will survive. So that way I will be able to find all the values for b. When I do that, I just realize that I have something special happening. So f at c is b0, f prime at c is b1, f second at c is 2b2, f third is 3 times 2, that's 3 factorial, b3. So essentially I can find from there the general shape. If I take the kth derivative and I evaluate it at c, I'll get k factorial bk. So from here I can find bk, I divide by k factorial both sides. So that's how we got the coefficient actually in the Taylor series. If you remember, the coefficient in the Taylor series is this part here. So that's how naturally it comes. So given a function, I can differentiate and get these coefficients. So this is the formula for the Taylor series, and given a function, let's say sine, cosine, tan, whatever I give you, and I give you also a center of the series, we can generate this straight directly. There is nothing special. And then we will use the ratio test to find the interval of convergence. So sometimes interval of convergence is all real numbers, which is fine. There's nothing wrong with that. What happens is if I stop, so you see here the series is we keep adding the terms forever, but if I stop at some point, I'll have a polynomial of certain degree. So if I stop at n, I'll have polynomial degree n right here. So that polynomial is called Taylor polynomial of degree n for function f centered at C. So big name, but we just say Taylor polynomial. So this polynomial is useful to approximate certain functions in the neighborhood of the center of the series. We will see some examples for this. So that's why these polynomials are useful. So essentially, the sum of the Taylor series is equal to our function. Hopefully it's the function that we use to generate the series. So with the polynomial, when we stop at n, we have the remaining part, so that's called remainder. So essentially we would like to show that this remainder goes to 0 as n goes to infinity. That way our polynomial is converging to the function. So that's just technical thing which is useful. So here we have the result that guarantees that our series is converging to a function that was used to generate it. So I have a function f that has many derivatives, so infinitely many derivatives, and we have interval of convergence, and when the remainder is going to 0 on this interval, then the Taylor series that I generate from the function f is actually equal to the function f. Because we know we can take a function, compute these derivatives, we get a power series called Taylor series. We use the ratio test to find the interval of convergence, so we know the series is convergent to some function. Which function? Well, hopefully the function that we used to generate. And this is what we need. We need to show that the remainder is going to 0. Remainder being this part here. So I add first n terms, and then the rest of it is called remainder. When the remainder goes to 0, obviously, if remainder goes to 0, then the polynomial is converging to a function. So this doesn't change anything to our way to compute the Taylor series. This is just a result that guarantees that the function to which the Taylor series is converging is our original function that we used to generate the series. So that's the use of this theorem, essentially, just to guarantee that the function to which we converge is the function that we use to generate the series. This is the theorem that is useful to show that the remainder is actually going to 0. So remainder is equal to this expression. And now the last part is to show that this thing here is converging to 0 when n goes to infinity. The condition that we need to satisfy is that the derivative n plus 1 is smaller in absolute value than some number m on interval of convergence, so for x in this interval of convergence. When we have that, then we can immediately prove that this expression here goes to 0 when n goes to infinity, therefore the remainder goes to 0 also. We remember this part here at the beginning, the observation, x minus c to power n plus 1 divided by n plus 1 factorial. The limit of this is 0, so m times 0 is 0. So basically this will be guaranteed as soon as we have our derivatives in absolute value smaller than some number m on our interval of convergence. So we saw at the beginning that this series here, using the ratio test, is convergent, which means that the general term goes to 0. So the general term here looks like the term here, n plus 1, n plus 1, n in the exponent, n plus n here in the factorial. So it's the same shape essentially, so the limit here will be 0 obviously. So mainly what we need is just to show that the derivative n plus 1 in absolute value is smaller than some constant number on for x's inside the interval of convergence. So this part is crucial just to show that our Taylor series that is convergent is actually converging to our function that we used, function f, that we used to generate the Taylor series. The proof is there just for illustration purposes, so if you wish to look at it, it's fine. If not, it doesn't matter. So let's see how we work with this. So the question will be normally compute the Taylor series or Maclaurin series for a given function f. So if I say Maclaurin series, immediately you know that the center of the series is 0. If I say Taylor series centered at x equal 5, then you know what's the center and you know what to do. So here our function that is given is exponential x. Now all the derivatives of exponential x are also exponential x. That's very convenient. So that's first step to get the derivatives. Now we need to evaluate those derivatives in order to apply the formula, and we need to evaluate them at the center. Here center is 0 because we are using Maclaurin series. So we need to evaluate the derivatives at 0. So exponential 0 is 1. X minus 0 is x. So this is what we get here. So it's just straight application of the formula. So this power series here is Maclaurin series for exponential x. So I used exponential x to generate a power series here called Maclaurin series, and this is what I got. Now the next step is just to see what is the interval of convergence. For that we use the ratio test. So we use our general term for the series as we usually do, so there is nothing special here. We simplify, so we have x times this limit is 0, so essentially whatever the value of x, here limit is 0, so this series is absolutely convergent for all values of x. So the interval of convergence is from minus infinity to plus infinity, and we say that the radius is infinity. So basically this series that we got by using exponential x, this series is absolutely convergent for all values of x. Now it's converging to some function. Which function? So that's the last step. This is why we need our remainder theorem. So we know this series is convergent, it's converging to a function. We need to figure out which function. Obviously we suspect the function is exponential x because we used exponential x to generate the series. So basically what we need is just a little bit of work to see how it works. So here if I take nth polynomial, so I essentially stop at n, so nothing special there. The formula said the next derivative here needs to be smaller than some number. So then the derivative is exponential x obviously for all values. On any given interval, exponential x is smaller than the upper bound of the interval. This is a number obviously. So basically what that means is that this derivative here on any finite interval is smaller than e to power the upper bound of the interval, which is a number. So for any given interval we have a constant here. It might be a big constant, but doesn't matter, it's a constant. And then we will compute the limit when n goes to infinity, and we'll get that this goes to 0. We already saw this, so basically now we will conclude that the remainder is going to 0. So on any given interval, our series is convergent, and it is converging to exponential x because the remainder is going to 0 on any given interval. And again, this part here was observed from the beginning. If we have a series with this general term, that series is convergent by ratio test, which means that the general term is going to 0. So basically what we have shown now is we obtained Maclaurin series or Taylor series centered at 0 using a function exponential x. So series is there. That series is absolutely convergent. We used ratio test for that. And now the last part was it's convergent to what? We suspect it's convergent to exponential x, and we proved by showing that the remainder is going to 0 when we use exponential x. So basically that's how we know that exponential x is equal to this power series. Just an illustration, so exponential x is in blue, and if I take a couple of these Taylor polynomials just to see what it means. So you see, if I take polynomial degree 1, so 1 plus x, because that was in the series, polynomial degree 1 is x to power 1, right? 1 plus x. I get this straight line, so this straight line is approximating exponential x, but on a very small interval. Now if I take polynomial degree 2, so Taylor polynomial degree 2, essentially what I do is I take the first 3 pieces here, so polynomial degree 2 is the first 3 pieces. Now my approximation again is red. It's a little bit better, so the interval on which this approximation is good, approximation of exponential x, is a little bit bigger than here. So what we observe is as the degree of the polynomial increases, the red curve is closer and closer to the blue curve, which means the interval on which the approximation is good is bigger and bigger. So higher the degree of the polynomial, larger the interval on which the approximation is good. So if I need to approximate exponential at 1, I can use the polynomial degree 4 here, and I plug, instead of x, I plug 1 and I get an approximation. Obviously, higher the degree of the polynomial, so more terms I use, better the approximation. Obviously, when we use infinitely many terms, we get exactly the function exponential x. As a curiosity, if I plug here, we already know that this equality is true for all values of x, so any real number. So if I put x equal 1, what happens? E to power 1 is e, and I plug here 1. Okay, so I get this series, and the series is actually 1 over n factorial, because if I plug x equal 1, so I have 1 to power k, so it's 1. So essentially I have the series 1 over n factorial, and that series is equal to the number e. So if I need to approximate e, I can add several terms of this series. More terms I add, better the approximation. What happens if I want to compute the Taylor series for the same function exponential x, but centered at 2? So instead of being centered at 0, now it's centered at 2. So all I do is I apply the formula. So it is the derivatives evaluated at 2, x minus 2 to power n, divided by n factorial. Now the derivatives of exponential x is exponential x, evaluated at 2 is exponential 2, obviously. So this is the series that I got. Using the ratio test, I can again show that this series is convergent for all values of x. And then again, using the same trick, I can find that this series, the remainder is going to 0. So the series here is convergent to exponential x also. Now what happened is here I have 2 different series for the function exponential x. First series was centered at 0. This series is centered at 2. I can pick any other number. Obviously I can take center at 75 and I get another series. So the Taylor series, each time I pick a different center, I get a different Taylor series for the same function. So that's very interesting. Now, what is the use of this? So I have one Taylor series called Maclaurin series here because the center is 0, but I can also generate another Taylor series with center 2 for the same function exponential x. Now, why do I need to do this? Well, it is useful to realize that from the graph that we already saw, more terms I add, closer I am. That's true. Now, if I want to get an approximation of exponential at, let's say, 0.5, well, 0.5 is close to 0, so center of this series is 0. So I could use this series to approximate exponential 0.5. So I could say, instead of x, I plug 0.5. Obviously, this goes forever, so I cannot compute forever. I need to stop at some point. So I could stop maybe using 3 terms or 4 terms or 5, depending on what I want. But closer I am to the center of the series, better the approximation. So this here is useful mainly when I want to approximate exponential x when x is close to number 0. So it could be negative 0.5 or negative 1, positive 1, something like that. Now, why is this series useful? Well, this one is useful if I want to evaluate exponential close to number 2. So if I want to find the value of exponential at 2.5 or 1.7, well, it is wiser to use this expression to get an approximation than to use this one. Why? Because here I will need less terms. So maybe to get a decent approximation I need 3 or 4 terms. Here maybe I need 10. So basically that's the general idea. That's why we have these different Taylor series centered at different values for the same function. The use is, if I need to approximate that function at a certain number, it is better to expand the series centered close to the number I am interested in. So we will see some examples for that. So the general procedure is apply the formula, use the ratio test to find the interval of convergence, and eventually the part that we should do, but most of the time we don't, show that the remainder goes to 0. So the Taylor series are useful, as we said, if I use partial sum. So instead of computing forever, I stop at certain power of x. So I use certain number of terms to compute an approximation to a function. So let's say I want to compute the Maclaurin series for a function sine x. So we remember Maclaurin series is Taylor series centered at 0. So what do we do? Well, we need to apply the formula. So this is the result. Let's see how we got it. So the formula said I need a lot of derivatives evaluated at 0. So I have my function sine. I need to evaluate it at 0. Derivative is cosine. I need to evaluate it at 0. Derivative of cosine is negative sine. Evaluate this derivative at 0. Derivative here is negative cosine. Evaluate it at 0. And again, differentiate, we get sine. So we realize we are going back to the beginning. So this is like a cycle of 4 steps. Okay? But look at the coefficients, because we are evaluate all the derivatives at 0. We have 0, 1, 0, minus 1, 0, 1, 0, minus 1. So those are the coefficients. So the formula was the derivatives divided by n factorial x to power n. So we just plug the values here. The first one is 0, the derivative number 1 is 1, derivative number 2 is 0, derivative number 3 is negative 1. So basically that's how we get this part. And then we generate a formula for the general term, because we see this is an alternating series. So since this is alternating series, we remember the formula for the error of an alternating series is the next neglected term. So that will be useful later on. So here I have power 1, 3, 5, 7. So power 2n plus 1. And downstairs is also 3, 5, 7 factorial. and then I have the changing sign. So the first sign is positive, so n to power 0, this will be 1. Then n to power 1, it will be negative, so that's fine. So the sign is correct, the general form is there. So that's a series that I got, Maclaurin series, that I got by expanding sign at x equals 0, or at center 0. Now the next step is to find the radius of convergence and the interval of convergence. How do we do that? We use the ratio test. So using the ratio test, what we realize is we have x squared and then limit of this when n goes to infinity, limit is 0. So regardless of the value of x, this limit here is always 0. So that means that by ratio test, my series is absolutely convergent for all values of x. So the interval of convergence is minus infinity, infinity. That means that this series converges for any value of x. So that's great. That means that this series is converging to some function, because this is function of x. Which function? Well, we hope it's sine x. It would be very unfortunate if it was converging to some other function. So here we have, our suspicion is that we converge to sine x because we used sine to generate the Taylor series. That will be always the case, by the way. But this is just an illustration how to use the result. So we said that if the n plus 1 derivative is smaller than some number, and the derivative here is sine or cosine, plus or minus. So in absolute value, sine or cosine, they're always smaller than 1. So all the derivatives are smaller than some fixed numerical values, some number. That condition guarantees that the remainder is bounded, and we know by the result from the beginning that this goes to 0. So basically, as soon as we have the derivative n plus 1 bounded on our interval of convergence, then we know that the series is converging to the function that was used to generate the series. So now we can say that sine x is equal to this power series, which is Maclaurin series here. So the process is very straightforward. Maybe the only long part is to get the derivatives, evaluate them, and recognize the pattern a little bit. Now I'll use again sine x, but this time I will expand around center pi over 2. So the center of the series will be pi over 2 instead of 0. So what we will get is a different Taylor series. So let's see how we get it. Again, we will need to differentiate and then just apply the formula. So again, the derivatives are there as usual. Now we evaluate them at pi over 2 because pi over 2 is the center of the series. So sine at pi over 2, 1. Cosine at pi over 2 is 0. Minus sine at pi over 2 is minus 1. So we see the coefficients that we will have. So essentially, the formula for the Taylor series is always the same, is the summation of kth derivative evaluated at the center of the series, here pi over 2, divided by k factorial, times x minus the center of the series, everything to power k. So this is a general formula depending on the center of the series. So essentially, all we do is just write it out. What we need is these numbers here for the derivative. That's why we computed them here, right? To see the pattern. And again, this is circling back, so the coefficients are repeating in the same order. So that's what we get. Some of the coefficients are 0. We see that for the derivative 1, 3, 5, 7, the coefficient will be 0. So things that will have derivative 1, 3, 5, 7, this will be 0, so that term will disappear. So that's what we have. That's why we have here only even powers. So now we recognize a little bit. So the power and the factorial, they are the same. So essentially we generate the term here, so x minus pi over 2. So the same power and the same factorial. We just need to, because these are even, right? So that's why it's 2k, because it's even. And then the first term was positive, so minus 1 to power k. When we start from 0, it will be 1, so that's fine. Just make sure that the first term has the correct sign, and then the other terms will have the correct sign. So now we got a power series, Taylor series, generated by sine x, centered at pi over 2. Now the next step would be obviously to show that this is convergent using the ratio test, so there's nothing special there. And then the last part is to show that the remainder goes to 0. So all we need to do is to show that the derivative n plus 1, which is either sine or cosine, is bounded by 1. So here is bounded by a constant, here is 1, so there is no issue at all. So that's the condition. When this is satisfied, we know that the remainder will go to 0. Therefore, what we have is that our Taylor series is converging to the function sine x that was used to generate the Taylor series. So normally this last part with the remainder, we usually don't do it because it's a little bit, it's either straightforward or it is more complicated. But it's very useful to compute the ratio test to find the interval of convergence. And again, more terms we add, better approximation. So here the sine x is in blue, and in red we see the Taylor polynomials, polynomial degree 2. So you see it's approximating well for a small interval around the center. And then higher the power, well, better approximation. Interval is larger and larger. Again, higher power, you see the red and blue are closer and closer, so the interval is increasing. Higher the power, larger the interval on which the approximation is good. So that's how more terms we add, better the approximation. Just for illustration purposes, we can also find the Taylor series for the same function sine x, but this time expanded about the center pi over 3. So you see what we will get, something extremely complicated. So this is just for illustration purposes. Obviously the procedure is the same. We compute bunch of the derivatives, we evaluate each derivative at the center of the series, so we get the coefficients. So what we realize is we have positive, positive, and then negative, negative. So the coefficients are the same, it's just the sign that changes. So then if we write this out, it's a little bit more involved, so we are not going to spend any time on this. The goal is just to show the special form, which is completely different from the other forms. So what we just realized is that the same function sine x has a couple of, actually infinitely many Taylor series depending on the center. So here the center of the series was 0, so that's called also Maclaurin series, and this is the shape. You see how simple and cute. If I have a center of the series pi over 2, we got a more complicated function, expression for the series. Now when I have my center of the series pi over 3, look how complicated the expression of the series is. Now all of these series are equal to sine x, and if I choose another center, I'll get another Taylor series for the same function sine x. So as we said, each time I change the center of the series, I get a new Taylor series for the same function. Now why is this useful? Well, we said this Taylor series is useful if we want to approximate sine x for number x close to 0. So let's say you want to know what is sine of 0.2. Well, it's better to use this expression, and instead of x you plot 0.2, and then you take certain number of terms and you get an approximation. More terms you take, better the approximation, obviously. Now imagine here, why is this useful? Imagine you want to know what is the sine of, let's say, 80 degrees. Well, 80 degrees, you need to convert it into radians. because pi over 2 is like 90 degrees, right? So I convert 80 degrees into radians and I plug x, the number that I get there. So this Taylor series centered at pi over 2, because 80 is close to 90 degrees, right? So that's why I would use this expansion here, because I will need few terms to get a good approximation. I could use this one also, but I will need many more terms in my polynomial in order to get a decent approximation. So closer I am to the center of the series, better the approximation. That means less terms in the series I need to pick in order to get the good approximation. So here, why is this useful? So pi over 3 is 60 degrees. Imagine you want to know what is sine of 50 degrees. You convert 50 degrees into radians, plug that number, sine of the number that you get, and you plug the number here and here, and you write a couple of terms. And you add those terms and you get an approximation. So that's why it's useful. So closer I am to the center of the series, better approximation I get, which means fewer terms I need to get a decent approximation. Just a remark, if I need to compute Taylor series or Maclaurin series for cosine, well, I could take the series for sine and differentiate it, obviously, because the Taylor series is a power series, so I can differentiate, integrate, I can do things like that. Obviously, we can expand the Taylor series using cosine x. Here it's Maclaurin, so it's centered at 0. We can do that, there is nothing wrong with it. But if we have already, in a previous question, let's say sine of x, we got the Taylor series for it, and the question B asks for cosine x, well, series for cosine x is just the derivative of the previous series. So we could use that directly. This is another example. We can generally ignore these binomial series. They are a little bit complicated. I'll just go through a couple of steps because they are kind of okay, not too dirty, but in general 10.4 you can ignore completely. So let's say we have this expression here, that this is a function, so we want to find Maclaurin series for this function, so we need to expand it around 0, so center of the series is 0. The procedure is what? Well, we compute a bunch of the derivatives and then we evaluate those derivatives at 0, because the formula says f, the derivative of f evaluated at 0 divided by k factorial times x to power k. Right? So essentially just the formula and we plug it. So from here we see the derivative n at 0 is just this term here. Derivative 3 we have k, k minus 1, k minus 2. Derivative 2 is k, k minus 1. So derivative 4 will be k, k minus 1, k minus 2, k minus 3. So that's how we get this. So that would be our Maclaurin series for the function 1 plus x to power k. Simple. Now if we need to find the interval of convergence, what do we do? Well, we use the ratio test. It's not a big deal. So the ratio test here shows that the series is convergent for x's in absolute value smaller than 1 by ratio test. So that's it. You don't need to spend any more time on these binomial series. It can get dirty and complicated for nothing. So we'll focus on more reasonable expressions. So 10.4 you can ignore it completely. Also 10.5 is just an application where we rewrite things in terms of binomial series, so 10.5 you can ignore as well. So let's see an application for these Taylor series. So getting a Taylor series is not complicated, it's just a little bit long because of the derivatives that need to be evaluated, but the formula is simple. We just plug the things into the formula and eventually we can find the interval of convergence by using the ratio test. We already saw that these Taylor series can be used for approximating the value of a function. So here is an example. So we will have two options essentially. So let's say here I have a function ln x, and I need to find a Taylor series, and I need to expand it about a center that I need to figure out what's the center. But I need to use that series to produce a polynomial degree 4. So I'll just take the terms in the series until I find x to power 4. So those are the terms that I need from the beginning up to take x to power 4. And the goal is to approximate the value ln 1.1. And then at the end we will estimate the error of that approximation. So ln 1.1. So what would be a convenient and wise center of the series? Probably 1, because 1 is close to 1.1. So if I have a center of the series at 1, it will help me greatly. So that's what I will do. I will use the center of the series 1, right? So I'll get my Maclaurin series actually. So I expand the series with the center 1. Obviously log 1 is 0, right? So there is nothing special there. The reason I chose 1 is because it's close to 1.1. I was asked to estimate ln at 1.1. So that's why I chose 1, because I know how to evaluate ln at 1 and its derivatives also. So the goal is to just apply the formula. Now they said they want an approximation using polynomial degree 4. So in front of the polynomial degree 4, the coefficient is the 4th derivative. So I absolutely need to reach up to 4 derivatives. And then they ask for the error. So the error will require the 5th derivative. So that's why I compute all the 5 derivatives here. So I have the function, and then I compute the 5 derivatives. And my center is 1, because that was the wise choice. So I evaluate each of these at 1. So f at 1, so ln 1 is 0. And then after that, I evaluate every derivative at 1. So I get these factorials here. So basically, this is the term that I will need to plug in my formula for the Taylor series. So the formula is there. So derivatives evaluated at 1 divided by k factorial, factor of k minus 1, 1 is the center of the series, to power k. So nothing special. I just need to plug this instead of f, the kth derivative of f evaluated at 1. So I'll have this baby and this baby downstairs, so they will simplify. They'll give me k only, and I have the sign here. This term is there. So essentially I get an alternating series. So this is the series that is converging to ln x. Okay, and it's centered at 0. Now we need to use ratio test to find the interval of convergence. If we use the ratio test, we will realize that x minus 1 in absolute value needs to be smaller than 1, which means x needs to be between 0 and 2. So that's a quick computation, nothing special. So we know that on interval of convergence 0, 2, our series here, the Taylor series centered at 1, is converging to ln x. So now they asked to use polynomial degree 4, so I add from this series, I add from 1 to 4. So I have my polynomial degree 4, you see here, x minus 1 to power 4. So I use the 4 terms at the beginning, so I have the power 4 here. So this is the polynomial that I will use to approximate the value of ln 1.1. How? Well, I plug instead of x 1.1 into this polynomial. You see 1.1 minus 1 will be 0.1. So all of these here, x minus 1 will be replaced by 0.1. So all I do is just compute using the calculator and I get an approximation. So here ln 1.1 is approximated by this number here. Now the last question is, what's the error? How good is this approximation? Well, we realize that this is an alternating series. So the alternating series, we know the error is smaller than the absolute value of the next term. What's the next term? It's 1 over 5, 0.1 to power 5. So 0.1 to power 5 divided by 5. Okay, so this is the error. So we have 5 zeros here. So that means we have first 5 digits that are correct. So that's the application. We find the Taylor series. They asked to use the polynomial degree 4, so we stop here when we have the power 4, and then we plug 1.1 into the polynomial. We get an approximation. We realize this is an alternating series, so the error is the next neglected terms, which is, so the term that comes after this is 1 over 5, 0.1 to power 5. So that error is smaller than that term. That's cute. Another way to compute the estimate for the error would be to use that expression for the remainder. We don't need to do that because this is an alternating series. There's no point of doing it. But just in case, this is just an illustration. So since this is an alternating series, I use the result from the alternating series. Another question could be, how many terms do I need to use in the Taylor series? So what is the degree of the Taylor polynomial that I need to use in order to get certain accuracy? So here they want error to be smaller than 10 to power minus 10. So again, we are using ln x and we are approximating 1.1. So the previous question was, use polynomial degree 4, get an approximation, and tell me what's the error. Now this question is, what is the polynomial that you need to use? So what's the degree of the polynomial, Taylor polynomial, that you need to use in order to get an approximation correct to 10 to power minus 10? So that's a little bit different, right, as a question. Again, since we know it is an alternating series, we can use the result from alternating series. Otherwise, we can use always the formula for the remainder. This is z is for, it is for the interval 1.1 because we are somewhere between 1 and 0.1. So if we don't use this, it's fine. We just use the formula for the alternating series, and that formula said it is the next neglected term. So 0.1 to power n plus 1 divided by n plus 1. So if I use polynomial degree n, I don't know what's the n. The next term will be with n plus 1. So this needs to be smaller than 10 to power minus 10. That's what they required. So now I need to solve this inequality. Usually we are able to solve, but in this case, no, we cannot solve this normally. So what we do is we proceed by trial and error. We substitute certain values for n. So we try n equal 2, n equal 3, n equal 4, and we go as much as we need, and we stop as soon as this expression here is smaller than 10 to power minus 10. So if I plug as, let's say, n equal 5, so I'll get 0.1 to power 6 divided by 6. I type this in my calculator, I get the answer. Is the answer smaller than 10 to power minus 10? If it's not, I need to choose a bigger number for n. 6, 7. So here it turns out is if I use n equal 9, then the resulting number here will be smaller than 10 to power minus 10. So that means I need the polynomial, Taylor polynomial degree 9. Okay, so here there is no other choice but to plug different values for n, 1, 2, 3, 4, 5, 6. Okay, so the first one that gives me the expression here smaller than the error needed, I stop. That's my minimum number of n, so that's where I stop. So here it turned out to be 9. That means I need polynomial of degree 9. So Taylor polynomial degree 9 to be used and evaluated at 1.1. So it's a lot of terms. And then I get the approximation using a calculator, obviously. I add all of these pieces. And I know that the error for this will be smaller than 10 to the power minus 10. So those are essentially the types of questions. Is given a function, find the Taylor series for the function centered at certain number, which is the center of the series. So we compute bunch of the derivatives and then we plug the value of the center into derivatives. We get some numbers and we bring that to the formula for the Taylor series. So that's essentially what we need to do. If we are nice, we should also compute by ratio test the interval of convergence, and that's about it. And then other questions could be, if we use Taylor polynomial of certain degree, let's say degree 5, what's the approximation of the function at some numerical value, like we showed in the previous example 10.6. And then usually we'll get that alternating series, so we can estimate the error immediately from there. Because we know for the alternating series, error is smaller than the next term in absolute value. And the other question that can be asked is, I would like to have certain precision, how many pieces in the Taylor series I need to use. So basically, what is the degree of the Taylor polynomial I need to use? What's the n? And again, we will get probably an alternating series, so we will be able to use the error for the alternating series is smaller than the next neglected term. And in this case, most of the time, as we saw, we will need to plug some numbers. Instead of n, we will need to find the smallest n that satisfies the inequality. It will be very rare that we are able to solve. Most of the time in this situation, we plug in the numbers for n. We try n equal 2, n equal 3, n equal 4, n equal 5. And as soon as we satisfy the first n that satisfies the error, we stop there. That's our degree of the polynomial. So that's pretty much the material for the Taylor series. Later on we will see some examples, solved examples.